Can anybody guess which open source project this code is from? So the point is, this is very authentic looking code, right? It's a proper function. It's written in C. It's got perfect comments. Every opened parenthesis is closed. Every opened loop is closed. Every variable is appropriately used, etc., etc., etc. It's very impressive. I'll tell you where the code comes from later. Same thing. So here's some math that goes with that code. And can you guess where this comes from, right? Looks very authentic, doesn't it? I mean, complete with, let's see, be a, with the crazy scripted character. Let C be a Gerber covering. Let F be a quasi-coherent sheaves of O modules. We have to show that something. Looks very authentic math, and just to convince you, have some figures and such like, which sort of show the relationships between the variables and the proof that you're trying to show. You have a couple of lemmas. The lemmas are properly numbered, and then you have a few proofs, right? All of this is fake. This one over here, a Wikipedia page which explains it all, right? Naturalism and decision for the majority of Arab countries capitalized was grounded by the Irish. By the time you get to the 10th word, this is nonsense. All of this has been synthesized from scratch by neural networks, and not very complicated neural networks either. In fact, these neural networks were rather simple, and you can find the code for it on Andre Karapathy's GitHub page. He has this article on the unreasonable effectiveness of recurrent neural networks. And it's phenomenal how powerful they can get, because these aren't the most fancy models you can think of. He's actually put up something very simple. This first one is the same code trained on source code from all of the Linux source code. He trains it on the Linux source code, and then he generates randomly text. And when he generates it randomly, it looks like perfect code. You have the comments, you have the variables in the appropriate case. Every open parenthesis is closed. Every open loop is closed. The indentation is perfect. The comments are perfect. Now think of the complexity of this task. So for instance, if I'm writing a function and I print a curly brace over here, how long do I have to remember that the curly brace was opened for me to actually do a good job, a perfect job of generating this code? This code will compile, and it waits until here to close the brace, meaning it has remembered this, right? You have a if. So once again, it has to remember that the if closes here. You have a for loop. It has to know the index, that the index is I. It has to do the right thing with the appropriate index somewhere in the code. Looks highly intelligent. It's a very simple recurrent neural network, right? This one over here, this is LaTeX generated once again by the same kind of recurrent neural network. It has been trained on lots of LaTeX from math papers, and it generates something completely plausible, complete with the figures. It seems to remember everything, right? So these this is not, of course, the state of the art. The state of the art looks something much more like this, which is astonishingly, convincing, right? Because one of the many sages of the time, the Bodhisattva Sakyamuni, with dates, was a popular religious figure in India and around the world. This Bodhisattva Buddha was said to have passed his life peacefully and joyfully without passion and anger. I mean, how much more convincing can this be, right? And this has been generated entirely randomly by a recurrent neural network, which is phenomenal. In this case, I don't believe it's recurrent, but still, the principles start off with recurrent neural networks. So what is the task that's actually being performed when you train this network? What is the task this network is actually performing? Here's what's happening. It's printing a bunch of stuff, and then the next character it prints is dependent on everything else that it has printed so far. If every task it performs, every time it outputs something, that is an independent task and it ignores the past, you would get garbage. So the fact is that it's the actions it's performing, the predictions it's making are based on everything else that the network has produced in the past. And it's doing an amazing job of it. So this sort of task is a task of modeling series, time series, text sequences of text, what have you. In all of these situations, one must consider a series of inputs to produce an output. And the output may either be a single value or the output itself may be a series. So for example, consider this. This is a speech recognition task and something has been said. The input is a sequence of spectral vectors. It has to analyze the entire sequence of spectral vectors before it produces an output. So in other words, you have this task where it has to analyze a series, a sequence of vectors, before it says anything. Or here's a different task. Here are a couple of different tasks. This is text. When you're analyzing text, you have the same situation. So the Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed, on average, 30 points a game and have shown no signs of improving anytime soon. This little blurb, I've been showing this for several years, and it has been true all those years. But anyway, this is after reading that, you had to figure out, observe that the word football is not mentioned at any point. After reading this, you've got to figure out whether it's about basketball or football. So you are performing a text classification task where the text itself, you have to analyze the entire sequence of text before you decide what is to be said, right? Before you decide the class. Or you could be performing a machine translation task where you read an entire sequence of English words, and then based on what you have read, you've got to go after you have read, so you have to analyze the entire sequence, you have to go ahead and output the same thing translated to French. So once again, you're analyzing a sequence of inputs and you're producing a sequence of outputs, right? Or here's another situation, predicting the stock market. Now the input is a sequence of vectors. On each day you have stock prices for a great number of stocks, stock indices, a lot of information on each day. And this changes from day to day. On any single day, if you are an investor, the decision you must make is, should I invest or should I not invest? And this decision may be about an individual stock, in which case you're trying to make a scalar prediction, or it might be about an entire portfolio of stocks, in which case you're trying to predict a vector. How much should you invest in every one of these stocks? And once again, this decision must be taken considering how these things have fared over time. So all of these are tasks where the objective is to classify or predict based after having considered a sequence of inputs, a sequence of input vectors. And the output you produce may be one or more. It may be a scalar, it may be a vector, it may also be a sequence. Now, obviously, prediction, classification, these are tasks that are very appropriate for neural networks. And so again, since we're talking about recurrent neural networks, we're going to see how we could do this using RNNs, neural networks. So before I continue, a little bit of notation. Now all the figures that I showed so far showed the inputs as being vectors, where typically you'd represent a vector in this form with many components, right? But then if I try to draw a neural network that's operating on a vector, then these guys would have to be connected to neurons. These would have to be connected to other neurons, and maybe there's a decision to be made. The figure would have to be drawn in this manner, right? But then I'd have to redraw the figure for every single vector that went in, which becomes a bit of a problem. So instead of showing it this way, I'm going to turn the whole thing over on its side and into the page, so that this vector is now going to be going into the page, and the network is also going into the page. So this is just like, I will be using this illustration repeatedly, so just to be very clear. This is what I mean. So this sequence over here represents my vector. I've just sort of turned it and sort of made it go into the page. And these are layers of neurons. In this particular case, the neural network is operating on a single vector. It's got 2 hidden layers, and then it's producing 2 outputs. But I'm not going to show the whole sequence of balls. I'm going to show it so edgewise. So anytime you see a square of this kind, this square actually represents an entire series of components going into the page. Anytime you see a little green square of this kind, it represents a series of neurons going into the page. And this little arrow actually represents a complete interconnection between the neurons in the 2 layers. And this is the notation that we're going to continue to use. So for example, if my hidden neurons over here were considering 2 vectors, if I were to draw the entire picture, it's going to look something like so. But once again, I'm going to draw it on the side. And so the actual illustration will look like this. Again, you must keep in mind that this box represents a sequence going into the page. So does this. And every arrow represents a complete interconnection. So just to drive the point home, suppose I had a network of this kind, which considers 2 vectors. You produce some hidden representation based on this vector, which feeds into some other hidden representation, which takes as input the first hidden representation and the second vector. This whole complicated structure, I'm going to show in simplified form like so. Again, every one of these boxes, the blue boxes represent inputs going into the page. The green boxes represent a layer of neurons going into the page, and all lines represent a complete set of interconnections. Right? So continuing on. Now let's go back and look at the stock market problem. So for the stock market problem, you have to analyze a series of inputs, and you have to decide whether you must invest or not. So in order to do this, to make a decision at this time, you have to consider what happened in the past. You have to look at the stock values, or the vector of stock values going several days into the past, ideally all the way into the past as far as possible, right? So how could you do this? What sort of neural network would actually look at a bunch of past values to make a current prediction? Anybody remember? We've just, Ankit, so cascade, oh man. So recurrent, no, but we've seen a network of this kind already. Yes, Kiran. A time delay neural network. This is exactly what you just spent 3 lectures on this, and you're working on a homework on this problem, right? Here's what I would be doing. So I'd have a network which looks at several inputs. This is what you've been doing, right, for your homework. And this, to make a prediction at time t at t plus 3, is going to look at t plus 1, t plus 2, and t plus 3, the inputs at 4 different times, and it's going to make a prediction. And then the same network is going to slide forward one day, and it's going to make the prediction at the next time, right? And so on. This is no different from searching for a pattern. This is exactly what we've been looking at all along. So this is a time delay neural network, just drawn differently, right? So this has an issue, right? This is a finite response system. What do I mean by a finite response system? Something that happens today is only going to affect the output for a few days into the future. So something that today happens today only affects the output of the system for some n days into the future. In other words, the prediction at any time t is going to be a function of the inputs at t minus 1, t minus 2, all the way until t minus n. And then if you go one step beyond, those inputs no longer affect the output. So if you were to consider what's happening at this red block, if the inputs at this instant, observe when it actually affects the output. At this time, it doesn't affect the output. Now it does, clearly. Now it does. Now it does again. Now it does again. And now it no longer affects the output. So as your analysis slides forward, the duration, the window of time over which any given input affects the output is very short. So so a prediction at any time only considers a finite window of history, right? So if I want to look further into the future, if I'm making stock predictions, it isn't enough for me to consider today and yesterday. I must consider today, yesterday, the day before that for several days. the further back I look, yes.
Oh, I was just wondering, so it's not explicitly accounted for, but since each day is explicitly just a function of the previous days, isn't it implicitly?
No, it's only the output, right? Because look at the output over here. This is literally what's happening. There's nothing going back. How do I go back? Right? So there's nothing going back. It's literally just 4 days, right? So if you want to increase the amount of time over which you consider the past, what is the easiest way of doing it? I just increase the width of the window over which I'll consider the input. So I could just be looking at to increase the history being considered. I could just increase this window, and it's not really a problem. I mean, it's not that big a deal. Our GPUs can fit it, nothing to worry about. But does this really satisfy what we need, right? Now, if you consider what actually happens in the stock market, you can keep going back, but today's stock prices are not dependent only on yesterday or the day before that or the past week. You have trends which go much longer. So you have, this is, for example, a stock market plot from, I'm not really sure when. This is, August 2014. I should change this at some point. But you can see these cycles. You have daily cycles, because what happened yesterday influences what happened today. But you have weekly cycles, because the stock market has some sort of a reset every Monday. And then you have monthly cycles. Then you have quarterly cycles, because every quarter the various companies announce their revenues. Then you have annual cycles. You have things that bust up during Thanksgiving and Christmas. You have lots of President's Day sales. You have these seasonal things that happen. So the trends, what is going to happen today, is predicted also by what happened exactly 1 year in the past, or not just 1 year in the past. If you want to make sure that this is not just a one-off thing, you'd have to look at what happened exactly on the 26th of February last year, and the year before that, and the year before that, and the year before that, for several years. So now, if I use this simple trick of simply extending my connections into the past in order to look further and further into the past, this is not going to work, because the number of connections you're going to make is just going to blow up, right? So the question we have is, how can I consider the infinite past when I'm making a prediction today without actually having infinite connections going into the past? And what would the obvious way be? Anyone? Antioch, what would the obvious way be?
I guess I'm not sure. I think maybe you would have some way to store the state.
You can have some way of storing the state. You want some kind of, what is the word for it? Ramal? Yes, Karan. Memory. No, you actually gave me an answer earlier, right? I don't know if you remember this. Yes.
You can pass the output over.
I can pass the output back in. The most trivial thing I can do is to just say that my prediction today is going to be a function of not merely the current input, but the output yesterday also. And if I do that, then what happens? An input let's say I have an input at time 0 and no additional input. Then an input at time 0 is going to produce some output at time 0. And now, because this is a function of the current input and the past output, even if I have no further input at time 1, because I have an output at time 0, I'm going to get an output at time 1. And so this is going to have recurrence. You're going to keep going backwards and backwards until you refer to all of time, right? So a single input influences the output for the rest of time. Now, this particular form of recurrence, where the output comes back into the network, is what we will call a Narks network. So, but then where are we storing the information about the past? How are we storing it? You know the hint. If I ask you a question, usually the answer is on the slide, right? So Michael, how is the output information about the past being stored? In the output, right? Thank you. Because that's where all the information is being stored, and the output is the variable that's carrying this information and being pushed back into the network, right? So Now, one of the characteristics that we wanted is that as you look further into the past, you want things that are in the remote past to have much lesser influence than something that happened in the immediate future, something that happened just in the immediate past. And a characteristic like this is likely to also satisfy this requirement under the right conditions. Anyway, so here's what a one-tap Knox network is going to look like. At any time, you have let's ignore this for the moment. You have some input. It's going to produce the next output, right? The current output. Then at the next time, the input is going to be the input here and the output at this time. These two are going to be fed in to produce the next output. And you're going to keep repeating this operation all the way to the end of time. So if I show you the entire sequence of computations instead of just animating it, this is what the actual computation looks like, right? This is the actual series of computations. But then observe that this is actually, what is this? This whole thing, when I just show you the entire sequence of computations, this is one neural network, right? Just as we did when we actually showed the scanning of pictures, and then I put all of them together in one spot, and we saw that this was just one giant neural network. Right? This is also just one giant neural network. What is the difference over here between a regular neural network and this one? This is one giant neural network where every column is identical to every other column. Right? That's the only difference. And here's the other thing. There is no direct connection from this column to this. The information is being brought in from the output. Now, I don't need to show it like so. This yellow box over here actually shows the output. The brown and the green boxes show the neural network components. The purple represents the input. So instead of drawing it like so, I can draw it this way. This just means that the output of this particular box is Y. It also is being fed back into the network, right? Just drawing it slightly differently. And so this is your Knox network. And it's storing information in the output, right? Now you can refer to the immediate output, but then you can also refer to other outputs in the past to look at longer term trends. So you could do something like so, where at each time you look at a bunch of different outputs and also a bunch of different inputs. So this is combining the time delay structure and the recursed output structure. And so the output at time t is going to look at some k past outputs and some l past inputs. Now a complete Knox network, if you were to just expand the structure out, is going to look at the infinite past and the infinite the outputs from the infinite past and the inputs from the infinite past. Obviously this makes no sense. Nobody is actually going to implement anything of this kind. But then when you begin talking about theory, it makes sense to begin looking at what happens at these things. But anyways, so this kind of network, which actually stores input, stores the information about the history in the output, is what we call a Knox network. And this turns out it's actually was a very popular model for time series prediction, like predicting the weather, like predicting stock markets, like predicting tracking, making predictions for tracking systems. Any phenomenon where that has a distinct sequence of innovation, something new that drives the output, is well modeled by Knox networks. The issue with a model of this kind is that there's nothing in the network itself that retains memory, right? The memory is bundled into this variable, the y, which the network is actually tossing out. There's no internal component of the network that's actually dedicated to storing information about the past. So let's modify the structure. Let's actually make this memory explicit. So if we want to make this memory explicit, we're going to introduce now a memory variable, and the memory variable's job is to remember things. That's all the memory variable is going to do. So the memory is going to be a function, some function, of everything that has happened in the past, which is to say that the output at time t minus 1, obviously that influences memory, the hidden states at time t minus 1, and past memory, right? Because you're aggregating memory, you're storing your memory. So you'd have a memory unit which is looking at all of these guys. And then when the neural network makes any computation at any time, it's going to consider not just the current input, but everything that was stored that is known about the past, which is the memory M. And so it's going to compute its hidden values H, and the output, of course, depends on the hidden value H, right? So in this kind of structure, we've introduced this memory variable, which is used to remember the past. This was also a reasonably popular model. And Michael Jordan is a famous professor in Berkeley who's made his name for all kinds of models on which are used for text analysis and latent variable models and so on. But his claim to fame was actually his work on neural networks, recurrent neural networks initially. And so this was his model, the memory neuron network, or the Jordan network, which was introduced somewhere in the late 80s. He just introduced this memory variable, exactly as I described before, except this memory variable itself was very simple. All it did was to maintain a running average of its past value and the current output. So the memory at any time was mu times the memory at the previous time plus the current output. And this memory influenced the hidden state at the next time. So because this memory is not really a learning process, how the memory is computed is not a learned process, there is no information being fed back. So when you're actually trying to train the model, if you are doing any kind of backprop, it's going to stop right here. There's nothing going further back here, right? Now, the issue with this memory is that it's actually, it's very simplistic. All it's doing is maintaining a running average of the output, which isn't a big leap from the Knox network, right? So along comes this thing called the Elman network, where the Elman network actually stores the memory, but the memory now is stored in a variable which simply clones the hidden state. And so at each time you produce your output, then this hidden state is cloned into this memory, and that memory is actually used to compute subsequent outputs. Now here again, because the memory is actually cloning the previous hidden state, there's actually genuine transfer of information through the network, not just through the outputs, but also through the internal variables in the network. But then the manner in which the thing was trained, you would sort of have this was your memory, right? Memory, the thing that stored the memory, and this you'd have subsequent portions. And this again was stored, and this would go on. And when you were training it, you would slice it up like so. So this would be a slice, and then this would be a slice. And then you treat each slice as independent predictors, where one of the inputs was the memory, and the other was the actual input being fed in. And then you would use these slices to learn the parameters of the network. So if you were performing back propagation, this is fairly straightforward, right? This is just an MLP which happens to have, two inputs. So again, there is no transfer of gradients going from one block to the other. Each block is being treated as being independent of every other block. So the story so far, in time series analysis, models must look at past inputs along with current input. And if you look at a finite horizon of past inputs, you get a standard time delay neural network, which is one variant of a convolutional neural network. Looking into the infinite past is not feasible using those structures. You need recursion. And so Knox networks recurse by feeding the output back to the input. And you can even feed back a finite horizon of outputs. Now you have these so-called simple recurrent networks, which actually explicitly try to model the memory through a variable. Jordan networks maintain a running average of outputs in a memory unit. And Elman networks store the hidden unit values in a variable and in a context, in what they call the context unit. Now these are simple or partially recurrent networks because during learning, each block is actually being treated as independent of the other. So the recurrence only occurs during the operational phase. The recurrence is not exploited during the the learning phase, right? So let's take a step back and look at how else we might do this. Now, how many of you here are electrical engineers? A small number. And how many of you have taken any course in controls? Quite a few, right? So the standard model over there is a state space model, right? The system has a state. The state of the system is going to be a function of the current input and the past state. And the output of the model is a function of the current state, right? So this is so you have HT, which is a state. You guys must have done it too, right? So the problem of being too close here, you get bypassed. So the state of the system is some function of the current input and the past state, and the output is a function of the current state, right? Now you can see how recurrence happens over here, because the state at any time is a function of a state at the previous time. So information is being passed forward, and the output depends on the state. So now this is what we will call a fully recurrent network. If I model these functions f and g as neural networks, this model itself doesn't assume that anything is a neural network. But if f and g are modeled as neural networks, this will be what we will call a fully recurrent neural network, or simply we won't use the term fully. We're going to drop it, and we'll just say recurrent neural network. And the state now summarizes the information about the entire past, right? So here's the simple state space model. The state at any time is determined by the input at that time and the state at the previous time, right? So let's say I have an input at time t. So again, if you were to just draw the computation, I cannot actually, because I have recurrence, I cannot draw each column independently of every other column. There's information flowing through continuously, correct? And so I actually have to show the entire sequence of computations this way. This is an entire neural network, but then once again, every column is identical to every other column, right? And now suppose I have an input at time 0. Then what we'll observe that even if I have no subsequent inputs, this is going to flow like so and produce an output at every time. So this is going to, the output at any time is now going to depend on inputs going all the way into beyond the horizon into the past, right? To make this model work, you need one extra term, which is that you need to define an initial state of the system. Look at this model. This h, once I go beyond t equals 0, there's this blue block. That's just the hidden state before time began. That also ends up being a parameter that must be set for the whole thing to work. Otherwise, there's nothing to feed forward, right? Questions? Yeah.
Do we always use one memory block for the past output, or can we use many memory blocks for many outputs?
Let's move on, and you will see. Okay. Now this, I've just used h as a generic representation for a state, right? So all I'm saying, what this little equation over here is saying is that I have some input, and the input is going into some state block which is feeding the output. I haven't actually specified what's inside the state block. That can be arbitrarily complex. So you could actually have multiple layers of hidden states of variables inside the state. If this is a neural network, you can have many layers of hidden values within this neural network, right? Now, so the state can be arbitrarily complex. So if I have to look at a recurrent neural network with a very simple state, where the state is just one layer of hidden variables, hidden neurons, this is what the network is going to look like. Again, every column is identical to every other column, and I have to specify h of minus 1. But then I can have a network with two hidden states, two hidden layers. Now this is exactly the same as this guy, or this is exactly, well, this is still the same as this figure over here. All that happened over here is that my state has been defined in a slightly more complex manner, right? or I can have something of this kind, where I can have skip connections across the neurons, across the layers in my hidden state, and that is also just an instance of this guy. All that happens is that the connections are a little more complex inside this block, right? Or I could have something like this, and this is also just an instance of exactly this model, where I have an input going into a hidden state, except that the hidden state now is a far more complex, and it has multiple layers of neurons, and the manner in which these neurons are connected to one another is a little more complex, but the basic idea remains the same, right? Now, I can take this one step further and do something like this, at which point this is not a standard state space model anymore. And why is that? Because now they have recurrence in the output, whereas the way we defined it earlier, there is no recurrence in the output, right? So this is a more complex version, and this actually begins to have the shades of a Knox network, because now I am actually saying that this guy connects into the state block at the next time, right? So now, in all of these models, you're assuming that the system at any time is only looking at the processes in the system and the variables of the system at the previous time. So there's a one-step recurrence. You're not restricted to having a one-step recurrence. You can have a multi-step recurrence, right, where you look at 2 times in the past. Now, again, you have to keep track of something here. Look at what happens here. When I have 2 hidden states, two hidden layers in my state, then these initial state values must be specified for every hidden layer, right? So also over here, the initial state values would have to be specified for every hidden layer. Here, I would also have to specify an initial output value, which could be 0. Here, when I have deeper recurrence, observe that I'm specifying these state values at t equals -1, but also at t equals -2, because all of these must be specified. The deeper the recurrence, the more the boundary parameters that must be set for the whole thing that must be for the whole thing to work. Yes.
In theory, doesn't the block already capture context about the past? So is there a need to have recurrence from
2 steps back? Yes. So now think about it this way. We'll look at this briefly in the next class. But if I have something along, I'll give you a trivial example. Suppose I say ht equals alpha times ht minus 1. How does a state value at time 0 change with time? If alpha is less than 1, it's going to fall off exponentially. That's it, right? Suppose I want a more complex mode where it fades first, then bounces again, and then fades later. This is never going to capture it. You're going to have to refer to the deeper time steps, right? So for example, if you wanted to cycle twice before fading, and if you wanted to cycle at, say, after a hop off, so this one is going to do something like this. This is time, this is h, this would fall off like so for alpha less than 1, right? But if I have something like some beta h of t minus, say, some capital T, then you're likely going to have something like that, right? Which it bounces again at capital T. So this deeper recurrence actually captures more complex patterns of memory. Make sense to you? Yeah. Yes?
Doesn't it become much harder to initialize that, because when you initialize things at different time steps, any implicit information that you're encoding in that initialization will be propagated forward?
As far as we are concerned, these are parameters that can be learned, right? If I were training this, I just go back, and these are all things that you would learn during your back propagation. Right. Anyway, so moving on, the simplest structures are the ones that are most popular. This is a very simple structure, just two hidden layers, right? Very straightforward. These tend to be popular, and again, all columns are identical, and an input at any time is going to stay forever, right? Now, when people actually draw these things, the illustrations tend to be very simple. So illustrations seem to tend to be figures of this kind. So this really means, if you look at a figure for a recurrent neural network, they'll draw something crazy with a loop going back. It doesn't mean that the output is feeding back into the same variable at the same time. It really means that it's going to feeding back to the same variable at the next time, right? Or you can have a more complex network of this kind where you have two hidden layers and you show these loops. So this means that the outputs are feeding back to the same variable at the next time, not at the same time, or something like so. You see there are two different colors of arrows over here. So the red arrows in this case mean that that's a self-recurrence across time. The black arrows mean it's in the same time, right? If I could also have this thing being fed forward into the next time, in which case I'm going to have to show this with a different colored arrow. So these are all just different ways of illustrating recurrence. So a model like this really represents a computation of this sort, where the hidden variable is always being fed forward to the next instant. Once again, keep in mind that every little square that I've shown represents an entire row of variables, right? Inputs or neurons going into the page, and every single arrow represents a complete set of connections. So this, for example, could be a k-dimensional vector. This could have some L neurons. So this line represents k times L weights plus L biases, right? Don't forget that. Now, suppose I have a network of this kind with two hidden neurons. And these loops, this figure actually represents a connection of this kind. The entire network is going to look like so. Or something like this is actually, this little simple figure actually represents this rather more complicated connection. We will sometimes call this the unrolled figure, which is like saying you take this figure and you keep rolling it across the page, and the rolling is, the arrows show the manner in which you unroll it, right? So what kind of computation is actually performed out here? Now look at this guy. This is the simple model with one hidden state, right? So there are two kinds of weights over here. One is the set of current weights, which is to say the weights that go directly up the connection, where the variable at any time which shows the dependence of the variables at any time on other variables at the same time. So those are the current connections. And then you have the recurrent connections, which show the dependence of the variable at any time on variables at previous times. So here, for example, you have 1 and 2, two sets of current connections and one set of recurrent connections, right? So what would the computation look like? The first hidden value is going to operate on an affine combination of the inputs and the hidden value, or the same hidden value of the previous time. So this H is going to be some activation F, which operates on a weighted sum of the X's plus a weighted sum of the H's at the same at the previous time, plus some bias, because that's affine, right? And again, observe that the bias is specific to this guy. These weights going from here to here are specific to this neuron, and the superscript 1, 1 shows that it's a connection from a neuron in the first layer back to a neuron in the first layer, right? So this would be the manner in which this output is computed, and the output Y is going to be whatever other activation which operates on an affine combination of the H's, which is simply a weighted combination of all of the H values plus a bias. Now observe that this is a weighted combination of several H's, indicating the fact that this guy is actually a vector of neurons going into the page, right? Let's look at this more complex figure. Now here, this H of -1 is part of the network parameters, right? The hidden value at time -1. Here I have two sets of hidden neurons, so both of their values for every component at time -1 must be specified. Now this again is actually, so this even at time -1 is going to be an entire row of values. So the number of parameters that I have to specify is going to be the number of neurons I have here in this layer plus the number of neurons I have here in this layer, all of those activations at time -1. So these are all part of the network parameters. And now when you actually perform your computation, this first neuron is going to operate on a weighted combination of the x's plus a weighted combination of its own activations at a previous time plus a bias, which is to say an affine combination of the x's and h1 at a previous time. H2 over here is again obtained through some activation which operates on some affine combination of h1s at the current time and h2 at the previous time. So you have these weights which show the connection from here to here. So the pre-activation value over here is going to be some weighted combination of these h's, where these are the weights corresponding to the combination, plus some weighted combination of h2 at the previous time, t-1, where these are the weights with which they're combined. So the superscript 2 shows that it's a connection from the second layer to the second layer, plus a bias, right? And the output, of course, is simply going to be, in this particular case, some activation, whatever it is, operating on a weighted combination of the second h values, second set of h values. So you see how the whole computation happens. Something like this is also going to be similarly done, right? Here, this first h is going to be some, once again, both of these values have to be specified at -1 as part of the network parameters. This first h is going to be obtained through some activation applied on some weighted combination of these guys plus some weighted combination of its own values at a previous time. This one is going to be obtained through some activation which works on a weighted combination of these guys and some other weighted combination of these guys and a recurrent weighted combination of itself at the previous time. And this output now depends on a weighted combination of these fellows and these fellows, right? So you can see how the computation is performed. Again, if you write it out in vector form, it's actually going to be very simple. Yes?
Can we have a connection between the second layer of the current time step and the first layer?
Sure, you can, right? So long as the connection is not loopy, it's fine. Right, so we did have an example of this way back when, didn't we? Like so. These are just different ways of implementing the same thing. There's often no reason to actually be doing these because it turns out simpler structures work just fine. But if you feel so compelled, there's nothing stopping you. So that's this one. So you get the basic idea of what a recurrent neural network is, right? Now there are several variants on this basic theme. Here's the simple one. This is a recurrent neural network with no recurrence. So there is no loop, which means that this is just your standard multi-layer perceptron. We know what it's good for, right? You can have recurrent networks of this kind, where I have a single input and then you have lots of outputs being produced. We saw examples of this being in operation, which was that. When we were producing the text, there was no input being fed to the system. It just produced stuff. You kick-started it with some random seed, and then it produced a sequence of text which looked perfectly plausible, right? So this is, or say image to caption. If you show it an image and you produce captions, that's going to be a recurrent network of this kind. Here's another recurrent network where you operate on a sequence of inputs and produce a single output when the entire sequence has been viewed. Speech recognition would be one example of that, where you look at the entire sequence of vectors and decide which word was spoken, right? Or you have the many-to-many. This is what we call the delayed sequence, what I call the delayed sequence to sequence. You look at the entire sequence of inputs, and then after some delay, sometimes waiting all the way until the end of the input, you go ahead and produce a sequence of outputs. So this is a delayed sequence to sequence computation. This would be useful, for instance, if you were actually performing machine translation, where you look at the entire sequence of inputs and then produce the entire sequence of outputs, right? And this is what we saw when we were performing the stock prediction, among other things, right? So different variates. So here's the story so far. Time series analysis must consider, actually I have a question about this to the lady over there, the one poking at her phone. Yes. What was this model again? We had an example for it. Do you mind turning your phone upside down? You there? Do you mind turning the phone upside down? Yes, thank you. All right. So, continuing on. Yes?
When we are dealing with text, wouldn't it be useful also to look into the future and not just in the past?
We have 4 more lectures on this. We will look at all of these, right? So, we're just sort of presenting the basic idea. So, time series analysis must consider past inputs along with current inputs, and looking into the infinite past requires recursion. We've seen that Knox networks achieve this recursion by reusing the output. Simple recurrent networks maintain memory or context units. The last bit we saw was that state space models retain information about the past through recurrent hidden states. These are fully recurrent networks. And the initial values for these hidden states are generally also learnable parameters, right? And state space models enable current error to update parameters in the past, and we will see how this is. For this, of course, we have to consider this issue of how do you train the network, okay? So we're going to use back propagation, but we're going to call this back propagation through time. And it will become apparent why we call this back propagation through time in a few seconds. What did we do when we performed standard back propagation? We started at the output and worked our way back to the input. There was no other way of computing the derivatives, right? Because the error was defined at the output, and then you had to push the derivatives backwards through the network. Here, what is the direction of flow of information? From the beginning of time to the end of time, right? So in other words, the derivatives themselves are going to have to flow backwards. So we'll call this back propagation through time, or BPTT. Now, to train this network, you're going to be given a collection of training data, which consists typically of a sequence of a collection of sequences. So each input is going to consist of a sequence of input vectors, x's, and the corresponding sequence of desired output vectors, the d's. Now, I'm going to assume for now that this is the structure, that you have a synchronous output for every input, because all the other structures that we saw can be thought of as simple simplifications of this model, where some of the inputs are set to 0 or some of the outputs are ignored, right? So this is the most generic structure. And so here, the network produces some outputs at every time. The network has some desired outputs at every time. And our job is to figure out how to train the network parameters such that the divergence between the desired output sequence and the actual output sequence is minimized. Now, so the forward pass, very straightforward. We know exactly how to do this. It's going to pass information through the network, pass the entire data sequence through the network. Here's the pseudocode for it. You'd start at time 0. You have, let's say you have initialized h minus 1. Then this is all in vector notation. The hidden value at the 0th layer hidden value is the same as the input, right? So at each point, the affine combination is computed as a weighted combination of the hidden values of the previous at the current time from the lower layer, plus a weighted combination from a previous time at the same layer, wt minus 1. The subscript r refers to recurrence. The subscript c refers to current, plus a bias. So this is just computing the affine combination at each time within the layer. And the actual output just simply applies an activation on the affine combination, right? And you would go through this, through all the layers. When you're done, you finally compute an affine combination of the output of the final layer, and then you compute your outputs. So this is just a straight up forward computation process. Now, you want to compute your derivatives going backwards, starting from the end. So that's why we call this back propagation through time. And the derivatives, just to simplify the figure, this figure is probably not clear because I have 2 arrows going into this box, right? So it's not very obvious what's going on. So I'm going to try to draw the figure like so. just to show you that there are, the actual inputs. And the divergence that we are going to try to minimize is not the divergence at individual times. The actual divergence that you're going to compute is the divergence between the entire sequence of outputs produced and the entire sequence of desired outputs, right? This need not be the divergence, sum of the divergence at individual times. So computing a divergence between two sequences need not decompose into the sum of divergences for individual symbols. This is something that you must burn into your mind. So this means that you're actually computing the divergence between this entire sequence and this entire sequence. This is not the sum of the divergences at individual times. So for example, if I were trying to perform speech recognition, the output is going to be a sequence of words. The desired output is going to be a different sequence of words. And these two sequences, if you try to compute the error, you're going to have insertions, you're going to have substitutions, you're going to have deletions. They are not one-to-one aligned, right? Which means that the actual error cannot simply be computed as the sum of the errors at individual times. So in general, the error that you're going to assume, you're going to assume that this divergence is not necessarily decomposable. It's an error between two sequences. That's what you're going to be minimizing, okay? In some special cases, we can assume that it will break down, okay? We'll get back to that. So here's how we denote it. The y's are the outputs of the network. Y of t is the output at the tth time. Here are all the variables. In this particular example, I have only one hidden layer. So the output of the hidden layer is h of t. The affine combination at the output I have superscripted with 2. It's z2 of t. The affine combination at the hidden layer, which is the pre-activation value for the hidden layer, is z1 of t. The inputs are x of t, right? So here's how I can compute the back propagation. The first step of the back propagation, I'm going to need the derivative of this divergence with respect to each of these outputs. Again, keep in mind that the divergence is a vector function of all of the outputs, right? So if you really wanted to compute the derivative of the divergence with respect to the y's, you're going to have to look at the totality of it. So regardless of the fact that it's a vector function of all of these guys, we know that you can actually compute the partial derivative of the divergence with respect to each of these outputs, right? So we know we can do that. Now, but the manner in which we compute this divergence can actually become challenging depending on how you compute, what kind of divergence function you use. And a lot of what we're going to do in the next couple of classes or 2 classes from now is actually going to focus on this issue of this, on the fact that this divergence is poorly specified in some problems, okay? But for now, I'm going to assume a special case. I'm going to assume that the divergence is a simple sum of the divergences at local times. So that I'm going to assume that you can compute a divergence at each time, and the total divergence is just a sum of the divergences at the individual times, okay? That's only for the sake of illustration. The actual arithmetic, the logic that I'm showing does not depend on this, okay? So if I do this, then I can say that the derivative of the divergence with respect to this yt is simply the derivative of this guy with respect to yt, right? It doesn't really matter. As far as we are concerned, eventually you have computed the derivative of this guy with respect to every one of these y's, okay? And now let's see how you would compute the back propagation. So now that I have the derivative of the divergence with respect to y, again assuming that I'm using column vectors as my notation, then the derivative, if my y is a column vector, right? So what is the derivative of the divergence with respect to y going to be? A column or a row vector? We've done this many times, guys. Kinjal, what's it going to be? The divergence is a scalar. The y is a column vector. It's going to be a row vector, right? So the derivative of the divergence with respect to y, yt, is going to be a row vector, right? And then I can take a step down And I can compute the derivative of the divergence with respect to the z over here, z2. And how do I compute it? Remember, we just did the chain rule, right? How would you do this? You guys, how would you do it? In vector form. So I've got the derivative of the divergence with respect to yt, right? Which is going to be a row vector. What is the derivative of the divergence with respect to the affine combination z? Is that going to be a column vector or a row vector? That's also going to be a row vector because z is a column vector, right? So I must multiply this row vector to get the derivative of the divergence with respect to z, which is a row vector, which means I must be multiplying this by what? A matrix. What is that matrix? Because I'm trying to compute the derivative with respect to z. I've already got the derivative with respect to y. What is it that relates those two? The Jacobian, right? So Jacobian of the activation function. So over here, I can just multiply this by the Jacobian, and that's going to give me my derivative with respect to z. So that's basically all we've written over here. This guy over here, this represents the Jacobian. So we've taken a step back. Now I can take a step further back and compute the derivative of the divergence with respect to the activation of the hidden layer, right? Is that going to be a row vector or a column vector? It's going to be a row vector, right? Because we're using the column vector notation. How do I get that row vector? Antioch? No, I don't have an activation function between here and here, right? So what would I be multiplying that by? Anyone else? Kinjal? Just the weights, right? Because now I have the derivative of the divergence with respect to z. I have the derivatives of the divergence with respect to z, which is a row vector. And the chain rule, I want the derivative of the divergence with respect to h. H is it? Yeah, right? Which means this is going to be a row vector also. So I need to multiply this by some matrix. And in this case, my matrix is simply going to be the weight matrix, correct? So we know how to do this. So that's basically, just in case you guys weren't sure, I have it all here on the slide, as always. Now, when I ask you a question, look at the slides. Sometimes the answer is there. In fact, most times the answer is there. Okay. Now, so now I've passed my way back. Now, what am I missing? I need one more derivative over here. Which is that? No, but I'm going back at this point. The parameters I'm trying to estimate. I need the derivative with respect to the weights. What is that going to be if I were to write it here? What is the derivative of the weight with respect to the weight going to be? Over here. That has to be a matrix too, right? So, Michael, what was that? No, so again, so I want the derivative with respect to this weight. We've been through this several times, right? I have a variable y here. I have a variable y here. This connects to a variable z. And there's a weight over here. I've got the derivative of the divergence with respect to z, right? How do I compute the derivative of the divergence with respect to the weights? Multiply by the y. So, if I multiply this by a y, what will I get? This is a row vector. If I multiply this by the y, I'm not going to get anything meaningful. They're different sizes, right? So how did we do that? Remember? You guys?
Do you multiply by the weights transpose?
No, I'm trying to compute the derivative with respect to, trying to compute the derivative with respect to the weights, right? This was, again, just I'm going through this just so that you remember this. This keeps coming back, right? We've been through 6 weeks. At this point, you should be able to answer this with your eyes closed. So, what was it? Guys, come on, help me. We're stuck. Kiran. So we have this relationship, right? And so the derivative of the divergence with respect to z is going to be a row vector. And clearly that figures into your derivative of the divergence with respect to the w. And so we saw this, I'll help you, it was y times this guy. Remember? That gives you a matrix of the correct size. Y is a column vector, the derivative with z with respect to z is a row vector, the sum of the product of the two will give you a matrix. Remember? Right? Everybody remember that? We've been through that a few times. You girls remember? Yes? Okay. So, otherwise? Okay. So that's exactly what I'm going to show you here, that the derivative of the divergence with respect to the weights is simply this h times the derivative with respect to the divergence there. Very simple, right? Nothing fancy. So now I have computed the derivative with respect to the weights. I also have the derivative with respect to the output of this network, of this layer. I can take a step back, and now I can compute the derivative of the divergence with respect to the input of this hidden layer, which is simply going to be, what would that be? So that's out here, right? The derivative of the divergence with respect to h times the Jacobian for the green box, right? This is just a standard chain rule. You keep going back. And so that's going to give you this derivative with respect to the variable here. And then I can take a step further down, and I can compute the derivative with respect to this weights matrix. I use the same rule as before. That's simply going to be x times the derivative of the divergence with respect to z, right? Straightforward, nothing fancy. We're just using the straight up chain rule. There's one more parameter to compute, which is the derivative of the divergence with respect to this recurrent connection and the weights of this recurrent connection. And what is that going to be? Now here is the crazy thing, right? This is going to be the output over here at the previous time times the derivative over here, correct? And that is going to give you the derivative of the divergence with respect to the recurrent weight. But you've gone past only one time instant. Now I have to go back to the previous time. So where do I start? I start from the top again. I'm going to say I've initially computed the derivative of the divergence with respect to the yt minus 1. Then I can multiply that by the Jacobian of this guy here, computed at zt minus 1, right? And this should have been t minus 1, sorry. And then I'm going to get the derivative of the divergence with respect to this variable. Now here's the crazy bit. I can take a step back and compute the derivative of the divergence with respect to the hidden value at t minus 1. But then there are two ways in which this influences the divergence. One is going straight up, and one is going right. And so this derivative actually is the sum of two terms. The first is simply the path that comes right here, down here, which is the derivative at zt minus 1 times this weight, plus the derivative out here of, which is with respect to z1 at t times this weight. You see these two paths coming in, right? So that's the first change that happened. There was a second change that happened, which is that when I compute the derivative of the divergence with respect to this weight, that of course was simply this ht minus 1 times the derivative at zt minus 1. But that's only the local guy. I know that this weight is identical to the weight out here. So I'm actually summing the derivatives. Now I can keep going backwards. I can compute the derivative here, same rule as before, right? I post multiply the derivative with respect to h by the Jacobian here, and then I can compute the derivative with respect to these weights which again is simply going to be x times the derivative at z1. But because the same weights are repeated, I'm going to actually be adding the derivatives. Make sense to everybody? And so also for these weights, right? Now this one is going to be, the derivative of the weights here is going to be this output times the derivative here, which is ht minus 2 times the derivative with, z1 at t minus 1. But because the weights are being repeated, I'm actually adding the derivatives, right? Yes? No, remember that's we did the entire business with influence diagrams, right? That anytime I have a variable v which influences some other variable y, like so, the derivatives are basically going to be summed over every path through which they're going to be. The one influences the other, right? One component is a partial derivative. We have to sum the lot. So here, for instance, you have two ways in which this is influencing divergence. So the two derivatives are going to be summed. Which? This guy. Oh, wait. So I mean, I know what you're talking about. It's over here, right? So this one. No. Okay. That one I understand. Yeah. So right before where? Here or here? So over here, you mean? No, this is that's information coming in. I'm just computing the derivative at this location, right? That's about it. Right? So there are two paths coming in. That doesn't matter. I'm just computing the derivative with respect to that one variable. Right? And so on. Now I can keep going back in the same manner all the way to the beginning. And then finally, I'm going to get the derivative with respect to the h. Remember, h was a parameter as well, right? And this we just saw is simply going to be the derivative with respect to z multiplied by this weight matrix, right? So we can compute the whole thing going far backward. And so here's the actual backpropagation pseudocode. For the output layer, you'd first compute. Observe that I'm using plus equals everywhere. Why am I using plus equals everywhere? That's because the derivatives keep getting incremented as you go back through time. So you assume that all derivatives are initialized to 0. And then because there's recurrence and the parameters are always being repeated, the derivatives are always being incremented. And so the only thing I have is this derivative with respect to y, from which I can get the derivative with respect to z by post multiplying by the Jacobian. Then subsequently, I compute the derivative with respect to w, but it's incremented. It's h times dz. This is going to be the derivative for the bias is going to be incremented by dz, right? And then when I go back, this too is incremented. Why is that? Observe that this h could have been influencing the h at the next time, right? So when I was processing the next time, there would have been a derivative which came back here. And to that, the current derivative must be added. Right? Since I'm going back through time, time is going decrementing, right? There's always an incrementing that goes through as I go backwards. And I'm using the same logic all the way through the code. Right? Questions? Otherwise, questions? No? Okay. So that's your entire, and this can be generalized to any architecture. Now I'm going to go 5 minutes over. You guys are going to have to indulge me. Because I spent too much time on the backprop. Now, we looked at recurrent structures, where the recurrent structure always processes the input from the start of time to the end of time, right? The implicit assumption over here was that what happens now affects what happens in the future, right? But as far as analysis is concerned, what happens in the future affects what happens in the greater future. So what happens at t influences what happens at t plus 1. What happens at t plus 1 influences what happens at t plus 2, which means that what happened at t plus 2 informs about what happened at t plus 1. Right? You could be looking at the future to make your inferences as well. And so bidirectional recurrent neural networks exploit this dependence. Now, so here's how the whole processing looks. This has actually got a forward net which processes the input left to right. It's got a second backward net which processes the input right to left. These two are independent networks with completely different sets of parameters. This will have an initial value for h, which corresponds to this guy, right? This is going to have an initial value of h, but that's at the end of time, which corresponds to that guy. And so the way you would process the input is this. First, you would process the input going left to right. Then you would process the input going backwards from right to left, independently of what you did in the forward pass. And each of these two processes is going to finally produce a hidden representation of the input, right? So you have the hidden representations computed in the forward pass. You have the hidden representations computed during the backward pass. The output is actually going to be using both of these hidden representations. Yes?
How would you use the output of those representations? Because wouldn't you, in some cases, wouldn't you want to weight the forward representation more than backward?
So you're going to learn how the two are weighted, right? So here's what the actual computation is going to do, right? You'd have the forward pass. This is just the conventional forward pass. This is the backward pass. It's just the forward pass, but then going backwards through time. And then observe what's happening over here. The affine combination at the output is a weighted combination of the hidden representations from the forward pass with its own set of weights, plus a different weighted combination of the hidden representations from the backward pass with its own set of weights, plus a bias, and that's what you're actually applying the final activation on, right? So you see how the whole thing works. Now, and you can actually modify the whole thing. I mean, I've sort of written this with one code doing the forward and the backward, but if you're smart, here's what you would do. You're just going to write a standard forward recurrent network with its variables, and then you would first pass your input through the forward network using the forward network's variables. Then you'd flip your input left to right and pass the flipped network back through the forward network, but now using the backward network's weights and variables. And now once that has been computed, you're going to flip them back to get them in the right time order. And then you can do the rest of your computation as before, right? So very straightforward. And now, how about training now? Here's your complete network, right? And you have to perform backpropagation through this. Now, this looks complex. It turns out it really is not. First step, of course, you need a divergence between the output sequence and the target sequence. And you're going to assume that from that divergence, you've actually managed to compute the derivatives with respect to all of the y's. And then you ignore the backward network and perform backpropagation through time to compute the derivatives for the forward network and update its parameters. Then you ignore the forward network and you compute backpropagation. Actually, it should be forward propagation through time at this point and update the parameters of the backward network. Okay? So, and you're done. So, if I give it to you as pseudocode again, I'm going to use a two-step pseudocode. Here is a little function which computes your standard backpropagation through time for a forward-only network, right? And then I can just, for the actual update, here's what I would do. I'm going to use the forward network to compute the backpropagation through time for the forward pass. Then I flip my input and use the same function, except now with a different set of parameters, to perform to update the parameters of the backward network. Right? So here's the story so far. What we've seen so far is that training recurrent neural networks requires defining a divergence between the actual and desired output sequences, which doesn't necessarily decompose into the sum of the divergences at individual times. Backpropagating gradients requires backpropagation requires backpropagation of gradients over the entire chain of recursion, and you will pool gradients with respect to individual parameters over time, right? The pooling is important. Bidirectional networks analyze the data both ways, beginning to end and end to beginning. And then these networks backprop must follow the chain of recursion and gradient pooling separately for the forward and backward networks. So we're going to be seeing in the next class, we're going to see what are the limitations, what are the things you have to worry about when you use recurrent neural networks and what solutions exist. And then in subsequent lectures, we will actually look at time series analysis, sequence to sequence conversion, and so on.